Welcome back to Chemistry 2, Unit 4 on Chemical Kinetics. We are on Lesson 3, which is integrated rate equations, and this will be video 4. In this video, we're going to look at a different order of reactions. So we're looking at second order reactions. So this means that the rate is dependent on the square of the concentration. So the integrated rate equation for this one is as follows. 1 over the concentration of a substance minus 1 over the initial concentration is equal to K times T. So for this one, we don't really have to define anything because there's nothing new from our first order. We do not have to worry about an ln. It's not in this one. So the half-life, again, if we let T equal T1 half, and A equal 1/2 A sub 0, then we end up with 1 over 1/2 A sub 0 minus 1 over A sub 0 is equal to K T1/2. So if we bring the 1/2 up to the top, we end up with 2 over A sub 0 minus 1 over A sub 0 is equal to K T1/2. And this ends up just being a subtraction of fractions because the denominators are both the same. So we end up with 1 over A sub 0 is equal to K T1/2. If we divide both sides by K to get T1/2 by itself, we end up with our equation T1/2 is equal to 1 over K times the initial concentration of our substance. So that is our half-life. So now we have our integrated rate equation that we can use, and we have our half-life for second order reactions. So we're going to look at our example problems. Here we're given an equation, we're given a rate equation, the rate law right here, and we're given a K value. And if we look at the K value, it looks different from our first order. We still have seconds to the minus first, but now we have molar to the minus first. There's going to be a clue there coming up. We know that this is second order because of that little 2 exponent right there, which tells us that NOBR is to the second power. So for number 1, how many seconds does it take to use up 1.50 times 10 to the negative third molar NOBR if the original NOBR is 4.00 times 10 to the minus third molar? So we're looking for time, seconds. We're given a K value. Our original concentration is given. This one is not our A value. This is our A sub 0 right here, but this is not our A because it says how long does it take to use up that amount. Our A value is how much remains. So we have to do our NOBR. 0 is 4.00 times 10 to the minus third, but our NOBR at time t is 4.00 times 10 to the minus third minus 1.50 times 10 to the minus third, which gives us 2.50 times 10 to the minus third molar. So make sure that you're reading the problems correctly. So let's put in our values. 1 over A, so 1 over 2.5 times 10 to the negative third, minus 1 over A sub 0, which our NOBR at original concentration was this, is equal to K, 0.810 M to the minus 1, S to the minus 1, times T, which is our variable. So we could either take the reciprocal of 2.50 times 10 to the negative third or put 1 divided by that. When we get that, we get 400. Minus 1 over 4.00 times 10 to the negative third is 250, is equal to 0.810 T. So 150 is equal to 0.810 t. So divide both sides by 0.810, and we get a t to be 185. Our units, we have to look at what our K value was and what time unit is involved in there, and that is seconds. So it takes 185 seconds for that to occur. So if we look at number 2, after 5.00 minutes, what would be our concentration of NOBr if the original is 2.40 times 10 to the minus third molar? So 1 over our concentration of NOBr, because that's what we're looking for. We're looking for this after 5 minutes, minus 1 over our original concentration, 2.40 times 10 to the minus third, is equal to K times T. Here's our T value, 5 minutes. This is in seconds. So make sure that you change 5 minutes to 300 seconds. If you don't, you're going to have a mistake. So we end up with 1 over NOBr minus 417 is equal to 243. So I just took the reciprocal of this value, and I took 0.810 times 300 to give this. So to solve this, I'm going to have to add 417 to both sides. So I get 1 over NOBr is equal to 660. And then we have to solve this for NOBr. So multiply both sides by NOBr and then divide by 660. So we end up with NOBr is equal to 1 over 660, which equals 1.52 times 10 to the minus third molar, or 0.00152. Our third example, what is the half-life of NOBr if we're given this original concentration? So our half-life equation was 1 over K times the original concentration. So all we have to do is put 1 over our K value, 0.810 m to the minus 1 s to the minus 1, times our original molarity. Our unit of molar cross out, we're left with seconds to the minus 1, which when we divide 1 by that brings it up top, and we end up with 4.94 seconds. So it only takes a little less than 5 seconds for 1/2 of this NOBr to decrease.